Hello. All right. So we're going to jump in here now to question three, or sorry, section 3.5. Do this. Go. So 3.5, 3.5. It's conditional statements and their converse. So we're going to introduce a couple of definitions here. Starting out, so we're going to look at what a conditional statement is. There we go. So a conditional statement is an if-then statement. For example, if it is Monday, then it is a school day. If you are in this class, then you are a Carleton Trail College student. So there's an example. Another example is if you are eating McDonald's, you are eating fast food. So the big part here is, oh, sorry, try to include the then. Keeps it simple, keeps it simpler rather. So big thing here is the if then. So this is a conditional statement. Okay. Couple other definitions we need. We also have an hypothesis. So this is an assumption, for example, in the statement. So if it is Monday, then it is a school day. The hypothesis is it is Monday. So this is the first part of it, okay? So hypothesis leads to conclusion. Okay? So this is nothing new from what you just got shown up above here, okay? So the hypothesis is the start of it. The conclusion is the end of the statement, right? So for example, again, if it is Monday, then it is a school day. The conclusion is that it is a school day, okay? So what would be my hypothesis for my first example with Carleton Trail? It'd be that you're in this class. The conclusion is that you are a student, okay? So I hope that makes some sense then. So that's why this if and this then comes true. Okay. So what we're going to do is I'm going to use I'm going to use this example here. So example one. There we go. Is verifying a conditional statement, which is, oh, sorry. I missed something here. Here we go. So here's example one. I want to verify whether, oh my gosh, whether this is correct. So we want to find out if this statement here is true. So James and Gregory like to play soccer, and regardless of the weather, their coach made this conditional statement about today's practice. If it is raining outside, then we practice indoors, right? Now you don't need to write this in, but the hypothesis, just kind of drive home that point, is that if it is raining outside, and the conclusion is that you would practice outdoor or indoors. So again, you don't have to write that down, but that's just really drive it home. So we want to verify whether this statement is true or false. And this is where I'm actually going to copy in this stuff here. It's going to be a bit of writing, and I do apologize for that. Pause the video, write this down, and then come back to it. You don't have to write down the stuff on the right, but it wouldn't hurt. So 3, 2, 1. All right, so we have 4 different cases here. So the first off, the hypothesis is true and the conclusion is true, right? So if it is indeed raining outdoors, and we are in fact practicing outside or inside, then that means that this statement is true. Okay. If the hypothesis is false, that means it is not raining outside. Then the conclusion is false. It's not raining outside, so we will practice outside, or rather, we will not practice indoors. So in that case, um, because the hypothesis is false, we haven't set it up, right? Because I'm not eating McDonald's, well, I clearly can't be eating fast food then. So in this case, um, is this true or not? Is this something that's actually true? Because the hypothesis itself is false. Because we haven't disproven his statement, because we don't have the chance, it's not raining, his statement is in fact true. Again, it's true unless we can find proof. Sorry, I guess that's a new concept here. Is it's true unless I can prove it's incorrect. Case 3 here, the hypothesis is false, so it is not raining outside, and the condition is true. It does not rain outside, and we practice indoors. Again, because the hypothesis is false, we can't disprove it. He's not breaking his promise. He's only talking about is if it's raining. Which case 4 here is, what if the hypothesis is true and the conclusion is false? So what if, hey, you're right, it is raining outside. That sucks. We're going to go practice outside anyways. In this case, this is false. Which brings us to our not our last concept, but our last major concept, which is a counter example. One example that disproves a statement is a counter example, and that means the entire statement falls apart. So you only need one. You only need one counter example to disprove a statement. For example, if it is, sorry, what was it? If it is Monday, then it is a school day. Hey, what about if it's the summer? What about if it's a holiday? This is false because, again, what if Christmas is on a Monday? What if it's summer? So on and so forth. If you're in this class and you're a Carleton Trails, I'll talk about those things later. So again, you only need one counter example here to be correct on this. So this is a lot to write. How would you do this if you were a student? Well, you would use something like this. You would use, we call this a truth table. Now, there's other ways of representing this. You can use like a branch in a tree, for example, which we'll get into. But this is a truth table. So in this case, so if it's P is our hypothesis, right? And we're going to say if it's true or false, right? That's what the T means. It's true or it's false. So if P, it's true. So it is raining outside. It is raining outside. And the conclusion here is true, right? Practice indoors. So if it's raining outside and we practice indoors, if both of these are true, the statement is true. Now, what does this stuff right here mean? What is it like? So first off, you're looking at this arrow, right? Now, I'm personally going to represent it as something like this. You know what? No, I'll do it like that. Here we go. That's what I'm going to represent that as. So this arrow here, this double arrow, this means P implies Q, or P leads to Q, or P, causes, or P causes Q, right? So again, what is P? P means it's raining outside. It is raining outside implies we practice indoors. It is raining outside leads to us practicing indoors. It is raining outside causes us to practice indoors. So these would all be true statements in this regard, right? Again, this is just taking this stuff up here, putting it into a table, right? When P is false and Q is false, the statement's still true. We haven't disproven P. P has to be true for us to possibly prove it is false. Okay? The hypothesis must be true to prove it is false. In this case, anyways. Maybe I shouldn't have said that. That might cause we'll figure it out. All right. So I hope that's making some sense here. Again, check, 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 X. Mhm. So I want to do I think I do. So you can represent this as a Venn diagram as well, right? So this can be represented with a Venn diagram because again, what is Q? So sorry, so P or the conclusion is a subset of Q, the hypothesis, right? And we can visually see this, right? We we practice indoors. So we can practice indoors, remember? So we practice indoors. If that's true, there's two cases where this is true, but only one of these leads to a false, right? So sorry. Yeah, no, I'm right here. I'm gonna remove this though, because I feel like that's gonna cause some issues here. So you can represent a conditional statement using a Venn diagram. The inner oval, right, the inside one, represents the hypothesis. The outer oval represents the conclusion. If P implies Q, P implies Q, then P is a subset of Q. Okay, so if P implies Q, then P is a subset of Q. The outer oval is the conclusion. The inner oval is the hypothesis here. And again, really break this point, only one counterexample is needed to show a conditional statement is false. All right, so get that down, and then there'll be one more thing to cover here. Here we go. So next, what if we have something called a biconditional? So what is a biconditional here? So this is when we have a conditional statement, right? P implies Q, whose converse is true. What is converse, you might ask? Now, it's going to give you a wordy definition, but we'll simplify it here in a little bit. So a converse is a conditional statement in which the hypothesis and the conclusion are switched. You reverse it, right? Reverse it. So a conditional statement whose reverse is true, whose converse is true. So for example, the converse of it is Monday. If it is Monday, then is a school day is, well, if it's a school day, then it's Monday. The converse of if you are in this class, you are a Carleton Trail student. Actually, we'll go. Nah. So if you are a Carleton Trail student, you are in this class. This is false. there are students in Weldon, in mining, in paramedic. They're not in this class. There are other Carleton Trail students who are not in this class. So this is false. Remember this example? If you are eating McDonald's, then you're eating fast food. What's the converse of this? Well, then if you are eating fast food, you are eating McDonald's. Also false, because I can be eating fast food, but maybe I'm eating Burger King. So that I hope that makes some sense there. What might be a true one? If it is a Saturday, then it is not a school day. This one's true. I can't think of anything to disprove it. At least, for our conventional school and the school we think of. So biconditional is, again, you can switch it and it's true. These are false because I switch this, it's not true. This one is biconditional. So again, yeah. So not biconditional. So this one is not biconditional. This one is not biconditional. This one is biconditional. Is that making some sense? So if you represent this in math terms, for example, what if, as we have a statement, if a number is true, hypothesis, P, then it is divisible. Sorry, if a number is even, then it is divisible by 2. Well, that's true. What if I take the converse? What if if a number is divisible by 2, then it is even. This is true. So this is biconditional. Right? So I take the converse is true, it becomes biconditional. So every biconditional statement has a true converse. Is kind of a rule here, right? It's not biconditional if it doesn't work both ways. So that's kind of this one here. Or sorry. If the converse, yeah, so we've done example 2 already. Like that is example 2 right there. This is example 2. It's just understanding how this works. I don't think we need an example applying it because that's just what it is. Same thing with example 3. I think we're good there. Writing conditional statements. Verifying a conditional statement, making a decision based on a conditional financial statement. I think you guys are truthfully, I think you guys are pretty capable of doing all this at this point. Because it really, if you understand the core concept, you just apply it to every example here. There's not necessarily in this case you do this example. In this case you do this example. It's all logic based in this case. So your key key ideas here. So a conditional statement consists of a hypothesis and a conclusion. And you can show this a couple different ways, right? If P, then Q. P implies Q. P double arrow Q. These are all the same thing. To write a converse of a statement, you just switch it, right? That would be that if Q, then P. And specifically, is it true? If it's true, if it's false, it's still a converse. If it's true, It's biconditional, okay? Sorry, it's not a Converse. My bad. Okay. So a conditional statement is either true or false. That's it. It's either correct or incorrect. That's it. Statement's true or false. Again, you can do a table here for it to work out. A conditional statement is false only when the hypothesis is true and the conclusion is false. Again, the conclusion, sorry, the statement can be true if the hypothesis is false. The hypothesis must be true for you to disprove it. Okay. Um, we've talked about this Venn diagram here. And it talked about biconditional. So we have the notation to show that P leads to Q. P implies Q. If P, then Q, right? That's this little bad boy here. Do I have something to show that something is biconditional? Yes. Just where the heck is it? Aha, here it is. So there's also this. Now, what is different between these? What is different? Double arrow. So P, double arrow. See that the arrows are going both way? Q. This is implying that it is biconditional, right? Okay. I think you guys are good to go now. I don't think I'm missing anything. I like you guys at this point can handle it all, I'm pretty sure. Um, if you don't know Sudoku, like I'm a math guy, I suck at Sudoku. So, don't worry about that. If you like Sudoku, have fun with it. This is all really tricky. This is applying a lot of stuff. Don't feel too bad if you're struggling with something here. Use your textbook solutions document that I showed you last video. It's going to be very useful for this stuff here. Okay, awesome.